Welcome to Physics 142 Online. I'd like to use our knowledge of Gauss's law to talk about some simple properties of electrical conductors and the electric fields inside them. You'll notice that the homework problems that we've done so far have all specified a non-conducting surface or a non-conducting object with charge on it. So now we'd like to talk about the properties of conductors. And conductors distinguish themselves by being the kinds of materials where charge can flow freely from one place to another under the influence of an electric field or a battery or something like that. So what we'd like to know, if there's going to be charge on a conductor, is where it's located and what special properties electrical conductors have. Gauss's law will help us answer those questions. But first we can deduce some very simple things about conductors by just imagining what happens if a conductor is placed in an electric field. So here on the right you'll see a slab that represents a conducting material, and the external electric field that's imposed goes from left to right, and it's marked with E. If there are free charges, that are free to move inside the conductor, and that's what a conductor has, those charges would feel a force in accordance with the electric field. And we know in the modern picture that the free charges in conductors are electrons. So the electrons, being negatively charged, would move to the left. They'd move opposite to the applied electric field. So the arrows with the little dots show the electrons moving to the left. So then free electrons would begin to pile up on the left-hand side of the piece of the conductor, leaving behind a net positive charge on the right-hand side. And what that does, the buildup of negative charge on the left and positive charge on the right, creates a new electrical field, E prime, inside the conductor. You might say that there's now the external field E and now the internal field E prime. So the net electric field inside the conductor at this point is E minus E prime. Well, more and more electrons will move, until there's enough electrons on the left side so that the internal field, E prime, equals E. And that would mean no more electrons would move, because the net electric field at that point inside the conductor would be zero. So no charges would move anymore. And that state is called electrostatic equilibrium. Equilibrium meaning the same force, no force. So those electrons would stop moving, and this entire process in practice is nearly instantaneous. It happens in just a tiny, tiny fraction of a second. So the net result is that the electric field inside a conductor in electrostatic equilibrium is zero, even though the conductor has been placed in an external electric field. So conductors are special because they respond. The charges inside a conductor respond in a way that will cancel out the effect of the external electric field. That's a special property of conductors, and we'll use it as we go along. Well, the second question is what happens if we put some excess charge on or inside a conductor? So if I frictionally create some charge and then put it in contact with a conductor, a piece of metal of some kind, what does that charge do? And there's two ways to answer the question. They give the same answer. One simple way is just to say that all those charges, let's say they're positive charges, they will repel and they'll move as far away as possible from each other, which means they'll end up on the surface. So that's a simple way to answer that question. Another way is to say, well, in equilibrium, as we've just talked about, the electric field inside the conductor must be zero. Otherwise, there would be charges inside the conductor that would be moving, and it wouldn't be in equilibrium. So once equilibrium is reached, that means the electric field inside is zero. Well, according to Gauss's law, then there should be no net charge inside the conductor. So if I have a conductor, let's say this oval-shaped conductor here, and I drew a Gaussian surface that's just a little bit smaller than the conductor surface itself, if the electric field on that Gaussian surface is zero, as we know must be the case, then inside that surface, the Gaussian surface, there wouldn't be any charge. So that's another way of showing that if we put charge on a conductor, or even in a conductor, it will move so that there won't be any net excess charge in the interior. All of it will be on the surface. So the principle, reasoned out in two different ways, but equivalent answers, is that any excess charge on a conductor will always move to the surface. And that's an important principle. So let's use this information to now calculate the electric field near a charged infinite conducting plate. We did this kind of a calculation in the previous chapter for a non-conducting surface, but now let's look at a conducting plate. So this conducting plate then has a surface charge density sigma on the surface, and we want to find the electric field just outside. So the problem, if the electric field lines by symmetry we can deduce are going to point perpendicular to the surface for a very, very long slab of material. So these field lines won't show any of the fringing effects that you might have near the end of a finite slab. So we expect then the symmetry to be cylindrical. The electric field would be the same everywhere on the curved surface of a cylinder that has the wire that has this that's perpendicular to the slab. Okay, so the cylinder that's drawn here has its axis pointing along the field lines, and then we can see this desirable property that the n hat unit vectors will either point parallel to the field or perpendicular to it. And we're going to put one of the surfaces of the cylinder outside the slab and one inside, and we'll see why that happens in a minute. That will simplify the analysis. So we draw that cylindrical Gaussian cylinder, and we'll just say, instead of specifying a radius, let's just say that the top and the bottom have cross-sectional area A. So Gauss's law, in the form that we've written down before, looks like this. We evaluate the surface integral on the left-hand side first, and because this is a cylinder, we have to break down that integral into three separate pieces, three separate integrals, because the cylinder has a top surface, it has a bottom surface, and it has a curved surface. So we just have to look at the relationships between E and n hat on those three surfaces, simplify things, and we'll have our answer. So we'll go to the next slide here. Same thing is written down. Notice that on the top surface that E and n hat are parallel to each other. And that means that E dot n hat is just E, whatever the magnitude of E is on the top surface. So that's nice. The second thing to notice is that on the curved surface, E and n hat are perpendicular to each other. So E dot n hat is 0, which means the curved surface integral will go to 0. Now what about the bottom surface? The bottom surface is inside the conductor, and we know that inside a conductor the electric field has to be 0. So there won't be any flux through that bottom surface either, not because because E dot n hat is 0, but it has nothing to do with the orientation of electric field and n hat. It's simply because E is equal to 0. And so that means that the bottom surface integral goes to 0, leaving only the top surface to deal with. And we already know that E dot n hat is E on the top surface. So we get integral of E dA on the top surface. And once again, similar to what we've done in previous calculations, we reason that since every point on that top surface is the same distance away from the conducting slab, then the electric field magnitude should be the same everywhere on that surface. That means E comes outside the integral. So all that's left for us to do is evaluate the surface integral, and that's easy, right? Because integral dA on the surface just means add up all of the area elements to get the total surface area. So integral dA is the total area of that top surface, which we've called A in our sketch, which means the left-hand side is just E times A, where E is the electric field on that surface. So now the right-hand side of Gauss's law, to do that, we just have to find the net charge inside the Gaussian surface. And where will there be charge? There will be charge where that Gaussian surface intersects the conducting slab. Now we know that the charge on the conducting slab is all on its surface. And so there will simply be a circle on the surface of the conductor which has the same area A as the cylinder. So sigma times A will give us how much charge is enclosed in the cylinder. It's just the charge that's on a little circle of the same area as the cylinder sitting on the surface of the conductor. So we put everything together in Gauss's law for this simple example. The left-hand side we know is just E times A from the very top of the slide. Q enclosed is sigma times A. And so when we solve for E, the A's cancel out, which makes sense. We shouldn't have an answer that depends on how large the area of the cylinder is. So we get EA equals sigma A over epsilon 0. The A's cancel, and we get that the magnitude of E is sigma over epsilon 0. And again, the direction we already knew by our use of symmetry for this problem. So now we know that the electric field is sigma over epsilon 0. So in class, we'll do some other examples showing how the information that we now know about conductors in connection with Gauss's law can be used to analyze charge distributions on conductors in special situations. I hope this was a helpful introduction, and I will see you in class.